Welcome. You are about to view a recorded talk of the Mathematical Consciousness Science online seminar series. This seminar series aims to explore the role of mathematics in the scientific study of consciousness and hopes to connect researchers who have an interest in this topic. While every session of the seminar consists of a talk and discussions, the latter are not recorded and the following will only contain the talk. We hope you will enjoy it. For further information, please visit our website, seminar.math-consciousness.org.
As has been said, nothing in biology makes sense except in light of evolution. And if one is thinking about consciousness as a neural process with about 100 millisecond time constant, a question arises, is there anything like that but slower? The Bernard Baars picture is that unconscious cognitive modules join together in a tunable global workspace, or if you prefer, a tunable spotlight to address rapid fire problems of threat and affordance. If you look at other physiological systems in higher animals, you find glycan code, cellular interactions, milliseconds to hours, but the immune response, hours to days, tumor control, days to years, wound healing, minutes to 18 months, gene expression to the lifespan, institutional and social cultural group cognition, seconds to centuries. So I'm basically starting with the end point of the argument. There are other similar phenomena that not only put together work groups that shift focus, like the immune system. Immune system will address a wound, it will address a malignancy, it will address an infection, all at the same time in different parts of the body. But it's not fast. If you want to be fast, you can't have multiple workspaces. In fact, if you have multiple workspaces in consciousness, that's considered a very serious psychopathology. But the inference is that consciousness is a stripped down version of these other mechanisms. Now, if you provide ATP at a certain rate, the hydrolysis of ATP to ADP carries about 51 kilojoules per mole. That's hot. Neural processes absorb an order of magnitude more metabolic free energy per unit time than do ordinary muscular phenomena. You heat something up by an order of magnitude, you can make it fast, but you can't have many of them. Cognition. You can play games with it, but the essence of cognition, if you go after the Atman and Cohen study of the immune system, is cognition requires choice. Choice reduces uncertainty, and reduction of uncertainty implies the existence of an information source dual to that cognitive process at every scale and level of organization. That's a compellingly simple argument. It's hard to get around. But information sources can be ergodic or non-ergodic. Cross-sectional mean is the same as the time series mean. That's an ergodic system. For an ergodic system, you can represent source uncertainty as a, quote, Shannon entropy, unquote. For non-ergodic systems, each path has its own source uncertainty. And thereupon hangs much of my story today. if you're talking about information, you've only got 4 asymptotic limit theorems. Shannon coding theorem and a tuning theorem variant. You've got the source coding theorem. You've got the rate distortion theorem, which is a tuning theorem variant. And more recently, developed in the last 25 years, you have the data rate theorem that connects information and control theories for inherently unstable systems. If you come up with another asymptotic limit theorem of information control theories, you're going to be in danger of getting a Fields medal. This is hard. This is very hard. But the linkage between information and control theory, it intrudes because living systems they become inherently unstable because they face an inherently unstable environment for the most part. Night and day, that's one instability. Being hunted is another instability. Getting sick is another instability. The data rate theorem tells you how much information, control information, you have to put in to stabilize an inherently unstable information control system. I mean, this is the standard model. Here's your system. At time x sub t, you have your system parameters. At time x sub t plus 1, you have your system parameters. You have noise coming in, that is stuff you can't handle, how the road shifts in, you're driving down a twisty road at night, how the road twists. You have a controller that puts information in at a rate, say u sub t. The basic idea of the data rate theorem is that under these conditions at a quasi and non-equilibrium steady state, you can write a simple linear matrix equation with a noise term, so that your parameter state at time t plus 1 is the function of your parameter state at times t plus the control information at times t plus something from the noise at times t. What you do is you can take the Bode integral theorem and you can play with it, and you find that your information rate for control has to be greater than a base limit determined as the log of the determinant of a subcomponent having eigenvalues greater than 1. This is for non-equilibrium steady states. That being said, for an inherently unstable system that generates its own topological information at a rate h0, you have to put in control information at a rate h greater than h0 to keep the inherently unstable system under control. H0 will appear down below. There are other ways of proving this. There are more general ways. I came upon it using a rate distortion theorem proof that relies on the convexity inherent to the rate distortion function. And that's that gives you a general solution that's not dependent on some little model. Next, what is information? Is information entropy? Feynman and Bennett will tell you information is not entropy. Information is the form of free energy. And you take a page from Feynman, and this is what the page looks like. You make a little, this is Bennett's argument, you make a little machine. You can see the piston in here. Little machine will turn information into work. Information is not entropy, particularly for non-ergodic systems where the Shannon entropy doesn't describe information. But you can get there another way. This is for ergodic systems. We go to Ken Wilson's 1971 paper on renormalization and the Kadanoff picture of phase transition. You can let strip Z be the partition function of a system with parameters K1 to Km in volume V. The free energy can be defined as the limit as volume goes to infinity of the log of the free energy divided by the volume. Go to the Shannon-Macmillan theorem for an ergodic system. You can divide utterances of an information source into two sets. One, a very small hyperprobability set consonant with the grammar and syntax of the information source, and a much larger set of zero probability, not consonant. And you can write the source uncertainty as a limit, as the length of your statement goes to infinity of the number of high probability grammatical paths of length n. V goes to infinity, n goes to infinity. And that gives you a free energy. This is for ergodic. We'll get to non-ergodic in a minute. You can, as I did in a 2005 book, you define an entropy-analog in a standard way. This is this is Legendre transform of free energy measure, and impose the dynamics of a first-order non-equilibrium thermodynamics Onsager model. You have to understand, however, that you don't have Onsager reciprocal relations because you don't have micro-reversibility with information sources. Second, you can impose Wilson's versions of the Kadanoff model on H using biological renormalizations. That's what I did in 2005. And you get somewhere, at least in my view. But what do you do for non-ergodic systems that are likely to dominate the real world? Let's, for the moment, look at ergodic systems again, and we'll look at the information chain rule, the uncertainty of n information sources, the joint uncertainty of n information sources by the chain rule is less than equal to the sum of the independent uncertainties of each information source. If these are free energies, what you got is a second law result, that it's really hard to isolate information source streams, communication channels. It takes less free energy. Remember, you're feeding this thing with metabolic free energy for consciousness. Your ATP to ADP, which is hot, but still, it's going to take more free energy to keep these chains, these information sources separate than to allow them to interact. And evolutionary process has a way of making lemonade of lemons. If it takes less energy to let the information sources interact, maybe you can do something big with that interaction. And we build the cognitive cathedral with this, the evolutionary acceptation of a spandrel. If you know the spandrels of San Marco, it's an ecological evolutionary paper. So, scalarizing resources for an institution, which is the kind of thing I study now. You've got your resources involve the rate at which information is transferred between subcomponents of the system. You've got the rate at which intelligence or sensory information is received by the system. You've got the rate at which metabolic free energy, in a large sense, is supplied to the system. And we want to work with, initially, we want to work with a scalar index, C times H times M. There are other ways of doing this. You can take the scalar invariance of a 3x3 matrix and make a scalar index out of it. Working with the full vectors and matrices of Z, making Z either a vector or a matrix. You can do it. It just makes the math harder. We'll get to that. So here we go into non-ergodic systems. For non-ergodic information source, each path has its own uncertainty value. This cannot be represented as a Shannon entropy. So to get an entropy, we have to do something extra. We invoke a pseudo probability for path J in terms of the sum overall. These are all the high probability paths. What we have done now is we have imposed a groupoid symmetry breaking into two equivalence classes, a small one of high probability grammatical sequences and a much larger one of meaningless low probability sequences. And we sum over the high probability grammatical sequences. This is a groupoid symmetry breaking that gives you right off the Shannon-Macmillan theorem via phase transition. The problem is you want to make a temperature in terms of Z, of your index Z. You can't just write Z because it turns out you're going to have to derive this temperature function G of Z using various tricks. So the denominator, including an approximation by an integral, provides a partition function. And we have, just hand waving, we've imposed a symmetry breaking version of the source coding theorem, dividing all possible paths into a small set, an equivalence class of meaningful sequences, consonant with an underlying grammar and syntax, and a very large set of vanishingly small probability paths that are not consonant. This is a big deal. This is a big deal. Can we build an entropy from that partition function? Yes, we can. We can. There's the partition function. And there's F, your free energy. And we write it as H of G of Z. And ultimately, we're going to be driven to formal power series, but not yet. For the simplest model, H of G of Z will be G of Z. And that leads to a solution. G of Z is minus F of Z over the Lambert W function of order n of minus F of Z. We know what F is from, we'll get to that in a minute. We'll get to how to find F. But the appearance of a Lambert W function will show, I mean, when you do work on the random networks, you find the W function appears in determining the size of the largest connected component in a random network. This is going to be a big deal. But let's get there. What you do is, in terms of F, you write your entropy as a Legendre transform of F. You impose an Onsager first order model, saying that the derivative of the time rate of change of z is going to be ds dz, which is a function of z. Typically, f of z will be known. You know the rate at which you can supply z. So you can write f of z for the system. Then you can solve, finding an equation for f of z. Once you have an equation for the free energy in terms of an algebraic expression, you go back here and calculate your temperature. In the real world, things aren't going to be as simple as non-equilibrium thermodynamics. You're going to be dealing with power series. Which power series you're going to be dealing with? This is simple Onsager version. That's y equals mx plus b for a regression model. These are more sophisticated regression models. These you fit to data. Now, typically, dz dt will be given by something like an exponential. This is especially true for institutional cognition. It takes time to deliver a resource. You can go to, if you don't want to deal with a scalar z, you can deal with a vector z. And the math looks like this in first order. F, H, G, S, F, and so on are all scalar quantities. And the math works out, but it's extremely a pain in the ass. You can actually do something with this. If you take the partition function and you allow it to be approximated as an integral, you can look at the rate of cognition in terms of the probability that you are above H0, the rate at which your environment provides topological information for an unstable system. And you end up with a very simple cognition reaction rate calculation. Again, H0 comes from the data rate theorem. This is the rate at which your embedding environment, which is providing its own topological information that you have to overcome with control information determined by this temperature, G of z. If you play with it, because G of z is in terms of the W function, the Lambert W function, you get inverted U dose responses for cognition rates. You get the Yerkes-Dodson law. Yerkes-Dodson law is a big deal when you're dealing with institutions. I won't go into it. But there's another way of looking at it. If you have a number of cognitive submodules that are linked by crosstalk, and you can do a calculation, and there comes a point at which the crosstalk links these cognitive submodules into a largest connected component. And that's in terms of the number of nodes and the probability of their interaction. And you can, for a random network, you get punctuated accession to consciousness. For linked stars of stars of stars, they're all linked anyway. So the topology of your underlying network is going to determine your threshold of detection for a system of a single global workspace. So, this is a standard result. The important thing is the topological tunability of the threshold dynamics. In general, the appearance of Lambert W functions appears to imply the existence of some underlying formal network. But what happens when you can have a number of these networks simultaneously? There it gets interesting. This is what I've been interested in. And the argument is somewhat subtle. The internal modular network linked by information exchange is a topology depending on the magnitude of interaction between nodes. Define an interaction parameter, say a real number small omega greater than 0, and examine structures characterized in terms of linkages set to 0 if the crosstalk is less than omega and normalized to 1 if greater than or equal to omega. Each omega defines in turn a network giant component linked by information exchange greater than or equal to it. Invert the argument. This is where it's important. Invert the argument. A given topology of interacting submodules making up a giant component will in turn define some critical value, omega sub c, such that the network elements interacting by information exchange at a rate less than that value will be excluded from that component, will be locked out and not consciously perceived. That's the first step. Second step, you can have a bunch of those operating simultaneously. Then you end up with a bold-faced omega. You end up with a set of them, of these little omegas. The immune system engages simultaneously in pathogen and malignancy attack, neuroimmuno dialogue, and routine tissue maintenance. A public health system or any institution has work groups. Individuals may be members of a number of different work groups working simultaneously, interacting, coming to a joint conclusion. How do you do this? Well, simplest way is to take boldface omega and assume you can reduce it down to a scalar somehow. You don't have to, but for these arguments, we'll do it. And then what you do is you take your free energy construct from the previous section and you do what Ken Wilson did in 1971. This is a standard calculation. Script F you begin renormalizing into blocks of size capital R, given a field strength J, and you carry through the standard calculation. F is the free energy construct. Chi is your correlation length. And the trick is in F, in script F. The trick is in script F. For physical systems, as Ken Wilson argues, script F is always R cubed, the volume. For cognitive systems, script F can be a number of different functions. And what's curious is that Ken Wilson's phase transition arguments work with these biological renormalizations. That's done in the 2005 book. The trick here is, rather than using information source, an ergodic information source uncertainty here, you use the construct of free energy that was discussed above. And you get phase transitions in very complicated, multiple global workspace systems. These are the ones that are of interest to me because they described institutional failure. Strip it down, make it fast, and you get one global workspace that will follow some of these biological renormalizations. Now, these are y equals mx plus b statistical models derived from the four basic information control theory asymptotic limit theorems. Remember, you go back and Jesus, what do you do for S? How do you define your entropy off the free energy? Free energy sort of falls out, but defining entropy off the free energy is not easy. Some systems will have a simple entropy definition, other systems will not, and your resulting dynamics are going to be really system dependent using these statistical models. But the bottom line from my perspective is that all of these sudden phase transitions can be imposed through groupoid symmetry breaking in cognition. Now, group symmetry breaking in physics is so utterly fundamental. You go back to the primordial Big Bang, and you play games with the system as it cools. For cognitive processes, cognitive phenomena, you're dealing with equivalence classes of paths, developmental of cognitive paths. And you're dealing with symmetry breaking in cognition in terms of groupoids, defined by equivalence classes, not groups. Ultimately, if you do enough of this, you're probably going to find that you're going to need more general structures than groupoids. For example, small categories and semi-groupoids. But I do believe that a lot of the basic phenomena in cognitive process can be, as the basic phenomena in physics are described in terms of group symmetry breaking, that a lot of the phenomena in cognition and consciousness can be addressed in terms of groupoid or other related symmetry breakings. I mean, I can rant on about this. One does. Consciousness is not a panpsychic phlogiston or cognitivorous ether. I would like to know what asymptotic limit theorem integrated information satisfies. If I could figure that out, I'd get my Fields Medal. Consciousness is severely limited by the necessity of the 100 millisecond time constant, which requires an order of magnitude more metabolic free energy than other physiological processes. And you're probably going to end up with at most one consciousness shifting tunable spotlight. Immune system, gene expression, what goes on at the cellular interface with the glycan code. These things, I think, have a lot more going because they're slower. And of course, that's where I'm focusing my interest now. I think I'm going to leave it at that.